how many of you all had a chance to visit the RAPID Additive Manufacturing Tool Show? Trade show, a few. And how many of you have visited AMUG, the user group meeting for Additive? A few. Well, don't worry if you couldn't go, because we did. And maybe that's the excuse you need for IMTS. But so we thought if we go, we must show. That's just the policy I have. And so they're going to talk about some of the goodnesses they saw, some of the opportunities for adoption and trends. And so that if you couldn't go to the show, we went on your behalf. So with that, thank you very much.
Yeah, so like everybody said, we all went to either RAPID or AMUG, large conferences, and we're just going to show you some of what we saw, some of the new technologies, some of the exciting trends, some cool stuff, report out. You have some newer faces to OMIC, as well as some faces you've probably seen before from OMIC, so we're just going to go around the line and say who we are. My name is Will Watts. I'm an associate researcher here in Additive.
常台从 Additive Manufacturing postdoc.
Kyle McGann, Additive researcher.
I'm Sierra Rep. I'm also an associate researcher here.
Trent Lamont, I'm also an additive researcher here.
And David Eames, associate researcher here at Additive.
Okay, so I was one of the 4 who got to go to the RAPID trade show, which was super exciting for us, and especially for me as a relatively new employee here, being able just to see a lot of the different technologies that I've been talking about, and a lot of them that I've been able to use, and a lot of the advancements in the different technologies. And everyone was bringing their best. It was very exciting. So the RAPID TCT is North America's largest trade show for additive manufacturing. And there were over 400 companies being represented there. We did get to talk to so many of them. It was 2 days of straight talking for us. And it's kind of some of the general trends that we saw in this trade show, where parts were either getting much larger, well, build volumes are rapidly expanding with much finer surface finishes, or they're getting much smaller and more intricate. So it was one of those 2 directions. We also noticed a lot more better material. So with better inputs, we get better outputs, especially in additive manufacturing. And then we also saw a lot more vertical integration within a company. So companies are really trying to take control of their entire process from the powder to the final part, and being able to showcase that they can do a little bit of everything within one machine or within one system of machines. So those are kind of some of the primary trends that we saw while we were walking around.
Okay, thank you, Sarah. So let's talk about the first what we found for their industrial the research trend. First part, we just draw the conclusion directly. That's for the powder additive manufacturing. If you want us to make that success, we need to engineer the powder first. Suppose normally we call printing, this is just a process. Normally after we print that, it also have a lot of issues, like we have thermal residual stress inside, we need to annihilate, right? Or after the LPBF we printing, we have some porosity, we probably use heat to reduce that kind of porosity. So here under this part, we call that is annealing heat. That part is called post-processing. Core is about the post-processing, also have the pre-processing. What is that? It's basically how we editing our powder, how we pre-treatment our powder. So based on this, in the material science research, they always have that concept. What if every time we print, we always have to one more step, like a post-processing? Is that okay? We can, according to adjust our powder, according to adjust the recipe, the internal, the material ratio, or specific strength mechanism, tuning our powder in the pre-process. And then after we print that, the material we just ascertain the mechanical property is exactly reach the target. In this step, we don't need the post-process. So make our life more easier, right? 2 steps you can do that. We need like so many steps to keep on fix the issue from the previous issue, right? This idea always comes so long, but right now we still like looking for any company who can do that. So in this conference, the final one is Sandvik. They did a great job. They developing is exactly according they tuning their powder is 2 steel 55. They of course that's their specific recipe. They adjust the design their powder. Then after they print them directly, they generate the material, the mechanical properties exactly you can use directly. You don't need a post-processing like annealing. You don't need a heat. So that's a great outstanding outcome for the research. So which means your pre-processing, if you do that well, you don't have to do the post-processing. That's a very good outcome for that part. And then in the other part for the powder, we're looking for is traditionally we found powder is just for most of the powder manufacturers to do that. There are a lot. But what about like a specific unit, small amount of powder? I don't need so much. How we do that part? They always struggling for our like researchers because research we don't need like so many amount of powder, just small amount of powder to study about that part. But this year we go to the conference. All of the producers they are right now very nice. They try to like say like okay, if you want to design specific powder, we can also do that for you. Now the powder design, this demand is dramatically increased. So which means the powder manufacturer, their producer realizes this is a market for us to developing our powder. Give the one example also like a tungsten. Tungsten we know is very hard and very difficult to machine that because it's not only hard, it's also very high temperature to melting them. So either you want like a traditional like a LED or normal heat resource to melting them to make that challenge. And or either you just want to machine that, it's too hard. So if you want like machining or directly printing them, it's very challenging. So Sandvik this year, they just like, okay, instead of that, I just like generate some like a tungsten powder directly. Then how they make that, that's very interesting. They will work with another electrical beam 3D printer company called Freemelt. They use E-beam. That's a higher energy. Then they work together, so one company, Sandvik, they make the tungsten powder. Then the Freemelt, that company, they use E-beam to make that. So right now, we can surprise us, we can use the tungsten to do the 3D printing structure. So which means, for example, give you one example, is for the fusion reactor internal shell. That is need a lot of temperature and also need to suffer a lot of pressure inside. Most of the companies, especially in the beginning of that company, they want to design what if after the shell we're also adding some like a cooling channel to control the temperature. Because we already built the tungsten powder and right now we also can make that with the heat exchange structure according to the 3D printing. So all of that complex step, we can make that in one step. So that's a great outcome for the research, especially also for the in the future the manufacturing. So that's why we call class OMIC why we need the powder atomizer, we need to make the powder. So like in drive to the beginning of that topic, if we want the powder additive manufacturing to be success, right? We need the first step to engineering the powder first. So in this way, we make the powder good. We can save the following step, or we can do the fantastic specific job to print some new materials. Yeah. So that's the first finding we found in the powder data. Second is for the multi-material additive manufacturing. Create a lot of new ideas inspired by us. Is for most of the multi-material, I'm pretty sure anybody, if you go to the conference, when you mention, if some company mention, oh, we have a bimetallic or multi-metallic, most one of the alloy definitely is copper-based. Probably all of you guys realize, so why is always copper-based? One is copper, the other probably is the other alloy. Why that happens? Because copper have a good conductivity. So which means they want the copper responsible for control the temperature. The second metal responsible for the mechanical property to hold the structure. So that's why, especially that's application in heat exchanger, in the aerodynamic, in the rock nodal, that's specifically need like a bimetallic copper. Okay, I use the copper to cooling down, control the temperature. And then maybe we use steel, stainless steel, or we use the Inconel, the nickel-based alloy, to hold the structure. And how to join them is always very challenging. Like in the morning, Professor Saber is giving us the research study, right? That's very challenging. One of them is one of the issues for us is very difficult to approach for the, especially for the copper. Copper is a good conductivity, but if we use a traditional like a red laser, it's very difficult to print. Why? Is red laser, they have a long wavelengths. Copper itself do not absorb that energy. So maybe you give 100%, they just absorb 5%. So you have huge energy, it's just waste. They do not go into the copper directly. And this conference we found out in the DMG Mori, they turned very smart. Okay, because the laser, red laser, the wavelength is very long, so it's not absorbed by the copper. That changed into blue laser. So which means the wavelength is around 400 micro. So in this way, the most of energy can absorb by the copper. Then the problem solved. You can print the copper. So for here we can see that they use the LED blue laser and with the powder directly, LED powder to print that. They have a pretty good job and they can control really precise dimension. That's a very good approach for that part. So for here, we talk about how we join two material. That's based on the energy. We use the energy deposited on both of them and melting them. Then they stay in the liquid state, then cooling down. Two material is bound. Is there any other method we can do that? Instead of, okay, I do not directly deposit energy on it and melting them together. Then we found another interesting technology. Is from the grid logic. What they did, they use actually the traditional, we call that powder can heap the method. How we do that is basically, traditional is what we did is like we put a powder in a can box, then we use a heap to center them together in order to do that. So based on this concept, what they did is they use a 3D printer, each of the layer, they deposit a specific material without any like binding. They just like play the sand, draw the line specifically in specific area. Then you put the second material also close to the next layer. So just like a deposit powder directly on the layer directly. Over here, like a deposit the layer one by one, like a beautiful destroy that part. And the space, this part, they just fill in the zircon. So that's like a high temperature that kind of material. Even though in the, we use in the heat that situation, they do not melt to fill in the empty that space. Then we just layer by layer to fill in the can. Then we put it into the heap. So the hot isostatic press to center them together. Finally, they can also join the stainless steel and copper together. So that's a very smart idea. Compared with the traditional DMG Mori, we use energy directly deposited on the material and melting them, right? This time, hold on, you guys do not melting ahead. You guys just sit behind each other. Then I'll pull you guys into a heap. And finally, you center together. Yeah, exactly. We do not melt. We just like center. That's also a good method to join them together. So yeah, that's basically for the bimetallic material we found an interesting part.
So in the laser powder fusion world, thank you very much, we found that the trend showing that companies are diverging from the middle. There's a number of companies that are in the middle space. They've got that ground covered in sort of the 1 foot by 1 foot cube build volume. They've got really well-made machines that people are using in the industry, making all kinds of different things. And so to differentiate themselves, they're either going bigger. In the case of this Nikon 2 meter tall print, or this other one, also 2 meters tall, or wider, 1 meter by 1 meter prints. Or they're going smaller, this 3D microprint system where they're making incredibly small, fine detail using finer powder. So that's the world of LPBF at the moment. That's what we're being shown. And then another incredible technology we found was lithography-based metal manufacturing. It's been around for a while, but Incas had a really slick machine that they were using, showing how their process works. If you don't know about lithography-based metal manufacturing, it's a UV light resin print that has metal powder suspended in it. So you can make a part out of any metal that you can suspend and sinter. So this is an example of their green part, an example of how fine the detail is, the pen tip, the one ring there. They had gold parts and copper parts, and they had chainmail and meshes that draped really nicely. It was a very interesting technology. It's incredible, it seems, for cosmetic parts. Really, anything small and fine detail, this machine would seem to work really well.
Yeah, so another trend, we saw a lot of people were talking about defect inspection. You make a part, and because it's 3D printed, there are problems with it. So one company, Fujifilm, brought a just off-the-shelf ultrasound machine to inspect the parts, sort of as an alternative to CT. There's a little probe, spend in water your part, scan it across, and you end up with an image. This is very new application. They had one application where they could embed a QR code inside of it so you could see part tracking without some random person seeing what the part was or information about the part. So that was cool, but it's still very new. So this might be, in the next few years, we see more and more on this. Another couple of companies, AM Assurance and Phase 3D. This was very cool. They were taking images of an LPBF print before and after the laser, right? And so they were able to make, as the part was being built, a map of all of the defects of the part. So when the part's done, their software could give you a go, no-go on your part without you having to do all of your tensile testing, all of that, all your coupons. You can already know that's a bad part. You don't even have to go further with this. So that was a really cool piece of technology. Saw a lot of development there. Who's next?
So I know that Tronkai already mentioned a little bit about the DMG Mori, but I really want to highlight, because they had a lot of really great technologies. Obviously, we have our DMG Mori machine that has some really amazing capabilities, and they're just coming out with more machines. And we really wanted to highlight some of those. So as I mentioned a little bit earlier, one of the major things we saw was massive integration between different softwares, different components, different hardwares. So I wanted to highlight this one, which is a FANUC robot, which has been integrated into their DMG Mori machine for automatic loading, or for repeatable parts, or just to have lots of different accesses to an already multi-axis machine. And then also, whoops, wrong way. So what was cool about this, as I said, was this FANUC robot was actually inputting these different pieces into this tool holder just automatically within the machining operation. So because DMG Mori has additive manufacturing combined with machining capabilities all in one machine, this also had automatic loading into tool holders, just all in one process for really repeatable results. So we're seeing a lot of the scaling of additive manufacturing within a machine and within components for more rapid prototyping and rapid building. We also saw, as Tronkai mentioned, a lot of this multi-material prints. DMG Mori especially is working on this with their powder and with their DED components. So obviously we've heard a lot about multi-material already today, but that was just something really cool that we did see. In addition, just some additional fun things that we saw that stuck out to us. This was a Meltio copper structure. We saw a lot of copper prints. A lot of people wanted to highlight this, and I wanted to highlight this print specifically because of its really interesting geometry. So we're seeing a lot more complex geometry, complex structures. We're taking really any idea that you can think of and being able to 3D print it using a variety of different technologies. And having this availability really expands what we're able to do with additive, and with all the parts becoming more fine, all the surface finishes becoming stronger and better, we really are seeing less of the need for machining. We're still needing it, but less of a demand for it, so we're able to get more of these complex geometries that might not need to be machined as prevalently. We also saw a lot of really large parts. So I showed this photo to my mom, and she goes, "I didn't know we were 3D printing humans." This is a large-scale WAM machine, WAM part, so our wire arc additive machine, similar to our Geffertech. This was probably also made on a robot. So we're seeing WAM parts, but they're getting super detailed, so less of a need for machining, especially for these bigger components that might not need as much of a really tight tolerance, but if you just have a big part that you're trying to get made, WAM is a really great solution to this. We also saw, as I was saying a little bit earlier, just super production parts. So we're seeing additive really come to the forefront of production. Our Renishaw, we have one of our Renishaw machine out on the shop, which you'll see on our tour. But Renishaw is doing production parts. So this is showcasing additive being used to produce parts repeatedly with really interesting internal structures and really being used. It's no longer a technology where we're like, oh, additive manufacturing, that's in the future, no one's using that yet. This is being used and actually being used for production, for companies bringing in revenue with parts.
So just to highlight another couple of cool technologies we saw, Nikon, they are coming out with, and they have an LDED machine. Their next generation, we saw some prints off of it. That was this tube here, probably 1 to 2 millimeters diameter, and then there's a tube inside of that tube as well. You can see that as well. So very, very fine detail LDED in a system that they're advertising towards tool repair, where it's all enclosed. They can scan the part, automated, create the repair path, and then repair it. So that was a cool system. Seguino, we talked to them about their cavitation peening, water cavitation peening, for parts finishing on internal chambers. A really cool detail we heard about this was that if you slightly decrease the diameter of the bottom of the path, you actually get better flow throughout the entire of the path, and you're able to clean out and finish the entire chamber. And then we saw some really, as we said before, interesting materials being printed, such as molybdenum from Fremont. So that was really cool to see some of these really cool metals being printed. I think next we have AMUG.
So Kyle and I are going to move a little quick so we can stay on schedule. But the AMUG conference is the Additive Manufacturing Users Group, and so while RAPID is kind of a showcase of current solutions in the market and companies representing them, AMUG is the users of that equipment kind of showcasing and celebrating the advancements of the last year that they've had and kind of internal R&D efforts inside of companies utilizing additive equipment. So they met, and Kyle and I were sent, and we got to go to 16 presentations and panels in kind of an action-packed week and learn as much as we possibly can. This is our second time attending, and it seems like every time we go, we see something that we didn't actually know was possible. And so kind of to highlight how diverse this conference is, one of the keynotes was from Ryan Watkins with NASA JPL, demonstrating crushed lattices for terminal velocity landings for NASA missions. And then on the other end, we have Scarbo Performance Corporation showcasing their usage of additive in custom automobiles. And so not only are we talking at the very, very high end, cutting edge of metal additive 3D printing, we're also talking about great kind of applications usage and all sorts of stuff.
Yeah, some of the key takeaways we want to make sure that everybody here kind of gets a good understanding of. Some of the key industries that are being really focused on really adopting these technologies. Aerospace, defense, and energy, we'll go over those a little more in a second. As I think has already been said a few times, surface finish was a big topic of conversation, topic of things, of how to better get your surface finish. Obviously, any 3D printed part, if it's powder-based or whatever, you're going to have a roughness to it. If you want to, that can impact mechanical performance of the parts. So can we, machining is one option. The internal, the pinging of it, chemical machining, there's a whole lot of talks about that at both RAPID and AMUG. One big notice we did from last year to this year was there's less talking about what we're going to do with additive, and there was actually more work actually getting done, getting to see true applications, which was a surprising change over only a 1 year, because we keep hearing about before then even, it's like, okay, we're going to do these things. And then actually seeing true applications was really neat to kind of see some of the data coming out from those. And then, as it always has been, aerospace qualification is like the gold standard. We want to get additive parts into planes, and it still is not easy. We're still trying to get there, so it's still like that goal, keep that lofty goal we're pushing towards. So it was still a big topic.
We're going to fire through some key industries here really quickly. So of course, additive manufacturing want to push for lighter aircraft, more efficient aircraft with supply chains that make sense and are kind of sustainable for the long-term life of that. And getting 3D printed parts on airplanes is terrifying for most people. And so we don't have to look at, let's get the part on the airplane. We can always look at, let's make the forming tool, let's make the fixture, let's make the work holding. We don't need to focus on, it has to fly. Everybody would like it to fly, but we don't need to fly. Indirect manufacturing methods are still highly applicable and have shown kind of through a lot of these presentations we've gone to and work performed that those tools save a lot of money over the life of the tool as well. Defense is another great option, especially in unmanned aerial systems. The requirements for flight are a lot lower, and so kind of the barrier to entry is lower as well. But once again, we're talking about let's keep products we're making now alive into the future, and we're not worried about companies going out of business and not being able to get parts anymore, or kind of re-engineering and remanufacturing legacy components that are not available. And then energy, a lot of the same principles here. We want to make things fixable, we want to make things obtainable. When energy has their products down for repair, it is costing them hundreds of thousands of dollars a day due to the kind of situations and contracts they work under. And so additive can enable kind of faster uptime. So, developing and implementing 3D printed crushable lattices for space exploration. We have a picture of the lattice. I took a picture myself, and it was basically impossible to see because the lattice is almost see-through. It is so thin, and so it's a little bit of an optical illusion. But it's really talking about the advancements that additive has enabled, especially because we knew we could use kind of honeycomb lattices before for crushed structures, and they were very difficult to get linear behavior properties out of. But using additive manufacturing, we can then engineer our lattice and tailor those properties to the application. And so in this case, that application is launching a sample return vessel at terminal velocity down into the Earth. And so without these lattices, we were potentially looking at a much more expensive mission for NASA. We're also looking at scaling the future AM solutions for critical UAS missions. General Atomics was able to present and share on a lot of their work for how they're using metal and polymer additive manufacturing for their UAS systems. And it was very impressive to kind of see the vertical integration within their company and the approach that they've taken, and not only wanting to adopt additive, but adopting an additive manufacturing adoption plan. And so as a group, they've made the decision, we can't just say we're going to adopt it, we should adopt a plan to kind of structure how that will work. And then Siemens Energy presented a great talk on AM-enabled, no, not Siemens Energy, this was Eaton presented a great talk on AM-enabled high power density electrical machines, and these were for eVTOL applications. They were able to 3D print their copper coils for their eVTOL motors to enable cooling channels within the coil itself, which then allowed for much greater power densities. Now, these are not motors that would be applicable to ground transportation, as they're very expensive, but their weight to energy ratios are very high, which makes them great for eVTOL applications.
Some of the talks that I went to that I really found interesting, especially this one, LPBF capabilities for large critical aerospace components. GKN additive, or GKN doing tier 1 aerospace supplier, trying to qualify an additive process for a 1 meter diameter part, and what that takes entails. This is a build plate of a lot of different mechanical sample pieces, and this was before they even started printing parts. This is just to qualify a layer thickness in titanium, and they were doing multiples of these, so it takes a lot of just the testing before you even start making parts. It's still there, especially for that aerospace like we were talking about. One of the other really big things I took a focus on was the defense side of things. Defense is still pushing additive heavily. It's really, they're really doing a lot of the driving of the advancements in additive. And what does it take for that to be successful? Well, there's a lot of options for this talk, talking about small manufacturers trying to get into some of these defense contracts and things, and how there's different opportunities there. They, just a manufacturer can say, hey, we need to make these things, especially in like legacy parts. That was a huge topic of conversation. And there's people out there to help you get to these things. And if you have any questions about that, if your company may be interested in that, then come talk to me and we can go through it more. And then the panels, I thought, I really focused a lot on panels. And these, critical metals, now that we're having all these import issues and tariff things coming up, can these powders be onshore, the feedstock materials? There was a lot of topic conversation there, and honestly, there wasn't a lot of good answers on these panels. There were a lot of questions being asked, and a lot of people look back and forth, who wants to answer this one? Because nobody really had a good answer, so it's something that needs to continually be talked about and hopefully find some answers. For deployment, getting things as close to the front lines with 3D printers to solve problems. We're talking about one specifically, explosive ordnance disposal technicians with their robots be breaking while working on a device. They actually got approvals from the Army to say, hey, we can print and replace parts, plastic parts, right there. So you definitely want to be able to do that. As somebody who actually used to do that job, it was really cool to hear that was approved and you could fix a robot in the field, and that was approved, even though that's something I would have done anyway if it's that kind of situation, so I don't have to walk down on it. But, and then castings, forgings, tooling, that's really where a lot of the winning thing is, which brings me to the winning applications here. How can additive really help you within industry? I'd say early integration, like we're talking with the the unmanned aerial systems. From the start, ask, if you're in the design process, can additive help this process? And a lot of times it may not be the right answer, but sometimes it will be. And if you have questions on how you can help develop that, come talk to us. We'd be happy to help you along with that. And then tooling, like I said, if it's the work holding, if it's the casting development, they're using 3D print the sand castings. Investment casting is using 3D printed wax molds for that. And it's actually, I know that was a huge plus for the jewelry industry, really helped that along. And then legacy parts, that's where that's defense is really pushing that, or I should say government-wide is pushing legacy parts. How do we keep B-52s in the air that have parts that have been around for a long time? We may not have digital files and those kind of things. Keeping that going, that's driving a lot of that. So there are other applications, but these were some of the big winning ones from our talks. So now we've got a little bit of time left. This is a chance for you guys to ask us. Hopefully we'll answer any questions you have about additive in general, and if we don't have the answer, we'll get back to you as soon as we can with the answer, but yeah.